Assalamualaikum and every good day to all my panel. I, MUHAMAD AFI BIN AZIM, will present about my PSM project, Fall Detection System and Smart Power Utilization using IoT monitoring for photovoltaic system. At this time, solar photovoltaic PV systems are most widely renewable technology used to generate power. In this system, smart power monitoring and fault detection on the off-grid solar system is proposed and designed to improve the solar PV system operating more effectively. Since environmental condition, equipment interference, and change in parameter cause a problem in the system. A real-time monitoring system is required in this project to monitor the performance of the solar PV system circuit. The Internet of Things (IoT) is used in this project to directly observe the energy in the system via an application directly observe the energy. Also, this paper discusses solar PV system fault detection based on the difference in the voltage and current value measured during the usual and unusual periods based on parameter value. This project will reduce the time spent searching for the faults in the solar system. The results show the several categories, including open circuit and short circuit, are classified as fault in the system. In general, the fault detection system and smart power utilization using IoT monitoring for the photovoltaic system will focus on this project development. For the introduction, problem statement. First, physical fault can be internal or external damage. Second, electrical and component failure can cause a fault in the solar PV system. For the third, environmental fault should be considered in the type of the fault in the system. For the objective, they contain three. Firstly, to investigate fault detection system and power monitoring in the photovoltaic system. Second, to design and construct the monitoring of the photovoltaic solar system and the fault detection using non-MCU ESP32 microcontroller based on IoT application. For the lastly, objective to verify the photovoltaic monitoring, fault detection system, functionality and fault data. For the scope, first, this smart monitoring with fault detection will apply to a standalone photovoltaic solar system that means off-grid. Second, to receive and process and transfer data from the input sensor. The MCU ESP32 was used in this project. The Blink platform is used as a monitoring and notification system accessible via the internet from anywhere. Lastly, fault classification will be determined by comparing the real-time voltage and current reading to the parameters configure value. For the literature, they contain 5 previous studies that I have studied. For the first paper, IoT system may enable remote control of PV system, effective and quick fault diagnosis, maintenance, and the recording of the generation and perform data for the analysis. Second paper, the data is processed using a microcontroller from the Arduino Uno and send a serial input to the SIM900 GSM module. The system construct in this paper is capable of measuring and sending data logging and monitoring by the user via mobile. For the third paper, the design of photovoltaic module modeling in this project to perform simulation based on the characteristic and classification by observing and evaluating the voltage and current value. For the fourth paper, presenting about a human machine interface (HMI) screen was used as a monitoring platform display the real-time measurement in a solar PV system. For the last paper, the implementation of Internet of Things IoT solar panel monitoring for the maintenance and efficiency improvement through fault detection using ThinkSpeak platform. For the methodology, a block diagram is used to represent the layout and structure of the involved system. The design of the project will be described. The system consists of 2 parts, which are the input and output side. The input part includes a sensor, while the output consists of a 5-volt relay module. ESP32 is the main microcontroller in this project system as intermediate between the provider and received signal. The ACS712 current sensor, the water sensor, and the temperature sensor are used and powered by 5-volt DC power supplies. The sensors are installed between each component to measure the voltage and current in the solar circuit. To trigger the faulty in the solar system, in this project, 5-volt relay module has been used. The faults are identified based on the parameters value that has been determined. The Blink application serves as an IoT platform for storing and displaying data from the sensor device. Via a smartphone application connected to a Wi-Fi network, ESP32 data are able to be accessed. From that, the user of this smart system can monitor and notice if fault occurs in the solar PV system when operating. The pop-up notification interface has been created when the faults are detected on the wiring circuit. This project used the Arduino IDE software to create the program for this system functionality. For the result, figure below shows the solar PV system operating on a typical sunny day from 10 a.m. to 8 p.m. The system started recording this data. The sun irradiance might be one of the differences between this system due to the cloudy and sunny days while testing a solar PV system. Thus, the measured result may not be as accurate and illogical to compare when the current sensor and ESP32 had an issue with the current scale of current and pin analog problem. The results show this project data reading value on the solar panel, batteries, and inverter side. The result used the Blink application to display the solar PV system operating. Using a computer, the user can export the data stored from the Blink into MS Excel format. And then the graph chart is ready to be constructed. The parameter table value identified based on the testing that has been done to determine the maximum operating point of this system. The code program function will be used this parameter as a reference to classify the fault. The tolerance of this solar panel was plus minus 6% according to the datasheet of this panel specification. The graph showed the power able started to generate around 12:30 a.m. until 4 p.m. and recorded the maximum power of 8 watt that day. However, unstable current infect the power reading measured due to the ACS712 current sensor issue. The maximum current recorded in the system is 0.43 amp, since the high solar irradiance generated at that noon period. In this theory, the higher the irradiance, the higher the maximum voltage and current obtained. The voltage of the solar panel is easier to measure than the current because voltage can flow over the longer distance than current due to the lower resistance losses. The current value generated by the solar panel is too small, cause the current sensor to be unstable and not read exact value. For the normal state battery and inverter chart, show the voltage measure reading from the battery store and the inverter. The battery voltage value based on its specification is 12 volt 7 Ah, but after conducted test, it can reach a maximum of 13.5 volt. Similarly, the inverter voltage should be the same as the battery voltage because the inverter power is depend on the battery power since they are connected in parallel. The maximum value voltage measure reading by the Blink apps is 12.94 volt, while maximum reading of the inverter is 12.78 volt. For the short circuit fault, show a graph of the current at the solar panel module when a short circuit occurs. The fault occurs when the current value is over 0.6 amp, which is greater than the current value of the parameter that has been identified. A short circuit is only tested on the solar panel part because two panels are connected parallel. The push button fault test function was used to simulate it because it is harder to wait for it to happen naturally. Battery fault part. Faults are uncommon on the battery because this solar system uses a charge controller as part of the protection. However, this part of the battery can cause a fault if the terminal connection of the battery and charge controller are not made correctly, and more dangerous when a short circuit occurs between the connection batteries. Push button simulate the fault by disconnecting the battery and the charge controller wiring circuit. When this fault occurs, the battery charging time is interrupted because the voltage reading at that time was 0 volt. Inverter fault part. This project used an inverter to convert 12 volt DC to 230 volt AC power. The chance of fault occurring at the same as a battery because the inverter is directly connected. The voltage received by the inverter is the same as the voltage by the battery. A faulty connection between the inverter and the battery was demonstrated using the push button. Thus, the results show the voltage change on the inverter becomes 0 volt because the power source from the battery has been disconnected. And finally, for the conclusion, in conclusion, a fault detection system and smart power utilization using the IoT for the photovoltaic system have been developed successfully. This project has been chosen as a primary focus for developing an effective solar PV system. A fault detection method based on the voltage and current observed and comparison has been employed to identify fault of the solar PV system. Results show that this method can detect fault type for the solar PV system, although the chosen method achieves the expected fault detection objective. The fault detection and monitoring system need to be improved by replacing the sensor with a more sensitive and stable one.